Hello guys! Today we will write a program would find a path in a binary tree with extra information. What I mean about extra information. So, for example, we have this binary tree, okay? And this is the left subtree, this is the right subtree. And we want to find the path from 2 to 4. Okay, the path will be 2, 7, 6 and 4. Okay, and we can write this path, we can put it into the list. Okay, 2, 7, 6, 4, and this will be the path. But I don't want to find only the path. I want to find a node and the direction from which we go from this node. So if in this node 2, to go to 4 we need to go to the left, and I mark this here, 2 and left. And from 7, when we go from 2 to the left, we go into 7, and from 7 we need to go to the right, to the 6 we go to the 6, and from 6 we need to go to the left, and in the 4 we mark this as the end. So actually I want to find such a list of tuples. Okay, each tuple containing a node and the direction from which we need to go from this node. Okay, and in the previous video we already write the path function, which give us exactly this thing, simply the list which contain the path. Okay, of course it was wrapped in maybe. Okay, because where we can search for path which doesn't exist. So we need to rewrite this thing. If you want to look at how we implement these two functions, you can see this in the previous video. You can see link above and in the description also. I will put it there. So first of all, we need to rewrite a little bit this function to add some extra information in this path. Okay, and first of all I need to define a data type to handle our directions. I will call it direction, and this is a simple type which either the left, either the right, either the end, and I will derive in show and DQ for it, because I want to print it and I want to compare the values of it. So, and let's start with changing our paths function. Of course, our paths function will now return a list which contain tuples. The first element is of type A, and the second element is a type of our direction. Okay, and if in this case then they have an empty battery, it's okay, but we need to rewrite this. So if we have S as all subpaths. So when they look at the tree at the point of some node, they have subpaths above this node. And to build all the paths from this node, we need to every subpath at this node. But fuck, this is a noisy neighbor. And okay, S is subpaths. Okay, if subpaths we have no subpaths, that means that they in the leaf, and they need return don't a here. We need to return a tuple which contain a and mark the end. That this is the last node of the path. The next thing I want to do is to redefine this where block. I need to add here some I need to define a PL, which is all the paths of the left subtree, and all PR, which is all paths from the right subtree. Okay, and of course I will rewrite here PL and PR. Okay, and the next thing I want to do is okay, here I need to add this A not to all subpaths. I need to look at two of them, and for each of them, for left and the right, I need to add a different pairs. For left I need to add not A, I need to add a pair A and left, because we move from to the left from A. And for the right I need to add a tuple with A and the R, because we move to the right from A. So let's start from the PL, our PL, all paths from the left. And here I need to add a tuple with the A and the left mark. Okay, left constructor. Okay, and they need to do exactly the same thing to the right, with the right thing, with the right branch. We add the A and the R to the PR. Okay, I think this should work. So PL and PR. Okay, let's try to compile this. PHS, of course I do some errors in the syntax. I need to close my tuple here, and the module is loaded. And now let's look at our paths function. Let's run it. Paths tr, and you can see that they get all this information. They get all the paths, the directions from each node. which shows the direction in the tree. The next thing we need to do is rewrite our path function. Okay, so let's move to this point. First of all, let's run our paths with tr again and look at this result. We have a list of lists which contain tuples. First thing we need to do, we need to filter them. So let's look at the filter type signature. Okay, we see that we need some lambda function here to define, and this function will take a list. And they need to check this list that it contains our A element in the first element of the tuple. We need such a list. So we need at first to modify our list. Okay, we can map it with a first function, which will get us the list which contain only the nodes. And after that we need to apply the lm function to filter to check if our LMA in our list, and that's all. This expression should filter it. Will filter only the paths which contain our A. Okay, let's move it here. AT filter LT. So I will take type signature from here, and I need to change it. We need a node A, we need a battery which contain this type of node, and we will return maybe we will return the path if it contains and if it exists in this tree, and this path is represented the list of tuples with this type A and this direction. So but now we will write only part of the function. I'll command this type signature and reload my module to show what we have at this point. At this point we have some function which takes tree and produce and filter all the paths which contain this node. Okay, of course we need to take only one of them, and we can do this with list to maybe function. Okay, it will take the first element from the list if it's not empty. If you empty it, will return nothing, and if it's not empty, it will take us the maybe value with one element. So let's look at step signature. Yes, it will take a list and produce a maybe value with the first element of this list. If the list is empty, it returns nothing. So if we reload and look at and run our puff function, they can see that they got the just value with exactly one puff, and they need only one puff. So what we need to do next? And next they need to remove this tail, because we only searching for a B. Till the B node we need to cut this tail with D. So how can they do this? Of course, because we in the maybe type and maybe the functor, we need to fmap it, and for for value they need to apply some function which called take while. Let's look at its type signature. Take while. And we can see that they need to be able to apply this function. We need to partially apply it to some predicate. So I will call take while, and here I need to write some predicate. First of all, we need to extract the first element from the tuple. This means that we need the fst function. And second thing, they need to compose it with not equality function, which partially applied to a value. So we extract the first element of the tuple at the first, and then we compose it with the function which check that this element is not the A, not our final element. And while this happening, this function will produce us a new list. Okay, of course we will lose the last our point at this expression, and let's check this. Take while. Okay, I think I need parentheses here. Let's try. Yes. Let's try to call our function. Okay, I've got the A and L, but we lost our B. But we lost it, okay, but we know that this is the last element. Sorry. So we can add it to the end, and we know what they need to add. Okay, they need to add a and the end marker and data constructor of our type direction. So I think this will work. We can check this. Yes, it works. A, D, yes, it works. For these three, you can see these three, and this works for it. So we done. we will write this function. You may ask why you need this information and why I need this. We will talk about this in the next video. So push subscribe, push like, and write comments. And I think this all. I will attach a code in the gist, in the description. You can see it. Okay, let's remove these old functions. And reload our module. And thanks guys for watching. Don't forget to subscribe and push like button. Bye.